So yeah, this is our story of taking part in Pwn2Own last year, and also our incredible ability to use Microsoft Paint to create that as well. So yeah, let's get going. So just a quick agenda. Things we want to go through are just some of the background to us taking part in Pwn2Own. Some of the important bits we thought are around our bug hunting approach, sort of how do we find the vulns that we ended up using last year. Some of the tooling we used and how we try to approach automation, which will become a bit clearer in a bit. We'll go through all the vulnerabilities we found, how we chained them all together to create an exploit, as well. Well, really quickly then, who are we? So I'm James. I lead up the security research team at MWR. My main focus is around VR and reverse engineering and new management responsibilities as well. So trying to herd other researchers into doing cool stuff as well. A bit later we'll hear from Alex. He's an offensive security researcher at MWR, again primarily doing VR. So he's done things like Windows Phone 7 jailbreaks, did Pwn2Own this year against Safari, lots of mobile security as well. Yeah, we're pretty big on our mobile security, particularly against Android. So, a bit of background then around particularly our MWR's involvement in Pwn2Own. So we have a bit of a history with it. Back in 2014 we took part against the Samsung Galaxy S5 and the Amazon Fire Phone. So we were successful in both those categories, exploiting the NFC component on the Samsung Galaxy S5 and the Amazon Fire Phone, Fire a Man in the Middle attack. Actually, the Samsung NFC attack was hilarious. It basically, if you did a touch to transfer files, it just opened a web server in the root of the phone. So probably one of the easiest Pwn2Own wins ever. We took part again in 2016 against the Google Nexus 6P. So again, we found a vuln in the browser component. At the time, that was only a partial success, unfortunately, because a patch rolled out the day before the competition, which affected our exploit. A few days later, it was working again, but just not in time for the competition. But we'll take that. It still worked in the end. So we come to Pwn2Own 2017. And these are the two devices we decided we were going to have a look at. So we had two guys looking at the Samsung Galaxy S8, and Alex and I decided we were going to look at the Huawei Mate 9 Pro. So both flagship devices for both Samsung and Huawei. Reason we chose these devices? Well, Samsung, we've had a lot of success with them in the past, and their security is questionable at best. And this was, last year was the first time Huawei was part of Pwn2Own as well. So Alex and I decided, well, let's see how good they are. And so we decided to take a pop at that. So kind of an interesting part with both these phones, which you might not be aware of, is just how much comes with the device. And there's just an incredible number of apps that will ship with both the Samsung, Huawei, kind of a lot of these OEM manufacturers' phones by default. So we find around 200 apps by default installed on the device, which provides us with a massive attack surface, especially when a lot of these apps are made by Samsung and Huawei themselves. So for us, this kind of gives us a great starting point for taking part in Pwn2Own. Lots of custom apps, again, with questionable security. For those that don't know, so we heard this morning about Pwn2Own and ZDI, but I thought it'd be good to just go through the rules explicitly, because it's pretty difficult. So for Pwn2Own, you need to fully compromise the device. So that is, we need to be able to execute arbitrary instructions, retrieve sensitive information off the device. A full sandbox is required, so particularly on browsers, without any user interaction. So for the browser component, as an example, all you get is a link to click on to our web server. And then from that point onwards, no further user interaction is allowed. We have to fully compromise the device. So it's not trivial. Another interesting thing I think about Pwn2Own are some of the categories. And then there's a lot of attack vectors open for exploitation, but the same rules do apply. So, full remote code exec without any user interaction. But some of this, I think, the interesting bit is you can kind of see the expected difficulty for each category. So, from the prize money. So exploitation 5 baseband in the competition expected to be potentially the hardest target. For us ourselves, so we decided we were going to go after the browser category. Mostly this is from a lot of previous knowledge targeting this, lots of previous wins. And again, like I say, this is a click on a link, then we've got to fully compromise the device. One other thing I thought it was worth pointing out as well is some of the standings. So these are the standings from 2017, Mobile Pwn2Own. And you might think, well, why the hell am I showing you this? You came third. But actually, the two teams there, Tencent and 360, they invested a hell of a lot more into this than what we did. And they have teams of people. So for us, we spent 2, maybe 3 man-months total against both devices, whereas they spent significantly longer with significantly more resources available to them, which I think kind of shows that the approach we took for Pwn2Own is kind of a good one. It sort of demonstrates that we can find quite a lot of vulns pretty quickly that are also exploitable. So hopefully our approach is kind of winning, even though we did only come third, which is still pretty reasonable, I think. Okay, so one of the things I think it's important to show is sort of our approach to bug hunting. So it's all good and well us coming up here and saying, look at the vulns we found, but actually, how do you get to that point? And naturally, one of the first things we need to do when we're starting a VR project is just looking at that entire attack surface. And this is sort of our brain dump of what we think the attack surface on sort of a modern browser, modern Android browser looks like. And it's pretty big. You know, there's a lot of potential there to start looking at things, but you've got to sort of think about the fact that other researchers are looking at this. So if you think areas such as file formats or the JavaScript engine, you know, lots of people are routinely fuzzing those. You know, that's Google themselves, the wider security research community, you know, us lot, and finding vulns, reporting them. So it's no good us turning up to Pwn2Own with a vuln that's been found and patched the week before. That's not going to count as a win. And also there's kind of some difficulties around exploitation, which I'll cover in a minute as well, so particularly for memory corruption bugs. So for us, we decided we were going to just focus our attention on inter-process communication issues. Sort of, can we get out of the browser? How do we get out of the browser as quickly as possible and start attacking other apps? So like I said before, there's a lot of apps on the device, and a lot of them have questionable security. So can we jump from the browser into those apps and start attacking those instead? And like I say, with typical sort of memory corruption vulnerabilities, there's a lot of exploit mitigations that are slowly making their way into Android that we would need to bypass as well. So it kind of makes traditional exploitation a little bit more difficult, particularly in the timeframes we're working to. Like I say, we're sort of 2-3 months at most that we're going to focus on working on this. So that's going from getting phone through to full remote code exec. So we kind of wanted a simpler way to achieve the same effect. You know, how do we get to that? So the approach we take is looking at logic bugs. And they kind of have a few nice positives over typical memory corruption vulns. They're typically harder to fix and identify, purely from they're kind of sometimes seen as features rather than necessarily bugs, or you know, a developer might not understand what the feature it would actually allow an attacker to do. They're also typically more reliable. You know, again, we're sort of potentially using an app in the way it's supposed to be used, but to achieve things that the developer didn't expect. They're also architecture agnostic. So we don't need shellcode. We don't really need to know what memory looks like across devices. And, you know, for those in the blue team, they're kind of hard to detect as well. So, you know, like I say, we're kind of using the app in kind of the way it should be used, but to achieve bad things, or good things for our perspective. There's also quite a few negatives to using logic bugs. So the guys that compromised the Samsung Galaxy S8 last year, Rob and Georgie, they ended up using 11 bugs chained together. Now, that's, you know, it's questionable as to whether that's actually any easier. So going out, finding 11 bugs, chaining them all together, is that actually any easier than just going out and finding yourself a nice memory corruption bug and exploiting that? Well, that's questionable, I guess. they don't always tend to be very stealthy. So with the Samsung device, as part of our exploit chain, or the guy's exploit chain, there was a full reboot of the device. Now, all right, maybe your average user will just go, oh, that's crappy Samsung, I expect that to happen, but still, it's not particularly stealthy. And you'll see in the demo at the end for our Huawei exploit, the phone noticeably shifts apps. So, a user will notice. It kind of also requires a much deeper understanding of the application and how it works. So like I say, we're kind of abusing features of the app. But to abuse those features, you kind of really need to understand a lot on how those features work first. And it's also much, much harder to automate the detection of these logic bugs. Like, how do you fuzz for a logic bug? Or how do you automate any of this? Fuzzing is a well-known thing, particularly for memory corruption bugs. It's kind of a lot more difficult for logic bugs. But we'll go through some of the progress we made as part of Pwn2Own in a little bit. Just some tips. So if you guys are looking at taking part of Pwn2Own, it's coming up in a month or two. So you want to be able to find, when you're looking for logic bugs, to quickly find a number of apps which we could potentially exploit. But how do you prioritize those? So the first thing we do is we just look at all apps that are potentially reachable from the browser. That's where we start. We also want to be able to get to apps at some point that have reasonable permissions, so that'll allow us to do more on the device. I mean, it's not necessarily an issue for the initial foothold onto the device, but at some point we'll probably want to get to an app that allows us to do things. And also, grep. Turns out, yeah, still really helpful. So just grepping through the code base for dangerous words, so things like, install, update, file reads, file writes, that type of thing is just a really nice, quick way of finding apps that you could potentially then go on to exploit. So yeah, the tooling and automation that we used. So like I say, the tool sets we used are kind of focused down on what we want to achieve. So, what do we care about as part of this? And we care about browsable intents, and intents that we can hit from the browser, or what we can hit from other apps. And this just massively increases our attack surface. So, rather than just focusing down on what's in Chrome, we've now got what's in Chrome and also the apps Chrome can talk to. And then at some point, what we want to get to is then what those apps can talk to. So, you go from one app to 30, 40 that we can now hit. The other things we're looking at are things like the content that we can load in. So, things like unsafe web views, really old Android issue, but still quite prevalent, as Alex will touch on in a little bit. Can we do things like controlled file reads and writes, particularly over sensitive files? Again, kind of a well-known issue, but it's still being found out on apps, particularly from Samsung and Huawei. Other really old phones, or well-known about phones, are things like unsafe class loading. Is there any of that going on? And none of this is particularly novel, but the thing that we're looking to do is finding these phones, chaining them together to show that actually, together, we can get full remote code exec. And like I say, the key here is really to try and increase our attack surface as much as possible. So the things we're looking at are for things like intent proxy bugs. So that's the thing that allows us to talk to other apps. Are there any issues there that then allow us to do things we shouldn't be allowed to do? As part of Pwn2Own, you're on the same Wi-Fi network. So are there things we could potentially do there? SSL weaknesses and things like that. So for those that don't know about Android or intent proxies, this is just a code example. So in this code example, we control the package name and the URI that's being loaded here. And then we can follow these code paths and see what the application is trying to do. And then can we do things like, load a web view, do file reads, do file writes, that type of thing. So the tool sets we used as part of Pwn2Own last year is nothing particularly amazing, if we're honest. So we have an internal script that we use. So this just goes in, we plug a device in, run the script, it'll go away, grab all the apps off the device and decompile them for us. So Takes a few hours. Like I say, there's at least 200 apps on a device. But what this gives us is a nice directory full of apps that are off the device that we can then start grepping through, start looking through. Jeb's a pretty well-known reverse engineering tool. So once we start finding vulnerable or potentially vulnerable apps, we'll throw it into Jeb, start reverse engineering it, and starting to see how we might be able to get to that potentially vulnerable function. And like I said before, the always amazing and hacker-friendly grep. Again, just grepping through the code base, looking for dangerous words, and it turns up lots of potentially useful results. But this is very manual. This is an incredibly time-intensive process. And we kind of want to get to a point where actually, so we know what a potentially vulnerable function looks like, but we don't know if we can potentially hit it. And that's kind of the difficult thing. So can we go from a browser through to our vulnerable function in a different app? So what we tried to do then is come up with a tool that will do that. And we kind of just, to speed up the analysis, ended up using graph theory to find these vulnerable code paths. And actually, all of this is just based off Yearn, but we've sort of ported it over to work with Android apps. So we just knocked up a proof of concept just to see how effective it would be, using known vulnerabilities in some apps that we had built ourselves. So in the example up here that we can see, there's find everything that is called initially from an exported intent that we can reach, and we know we can reach, that also uses get external storage, and that also uses dex class loader. So at this point, we might be able to drop a file onto the SD card, and this app would then potentially load it, and we might potentially get code exec. So we can just pass that through. I mean, actually, this comes from a real-world example that we used as part of Pwn2Own. This is another example of how we potentially use the tool to map out relationships from onCreate. So onCreate in Android is the function from where an application is initialized. So if we try and call an application, we kind of want to know what it then potentially goes on to execute. In this case, a class load. Again, this is just a dummy example, but it provides us with a quick, easy, visualized way of potentially finding vulnerable code paths. So yeah, so there's a lot more. So Rob and Georgie talked about this in a lot more depth than I will do today in their presentation, Chain Spotting. Well worth checking it out. So that's how they went about and compromised Samsung. The other tools that we'd very much like to touch upon are dynamic analysis tool sets. So big ones for Android are Exposed and Frida. To be honest, we mostly use Frida just for preference. But that's kind of an example there. So Exposed, that you can do things like early injection and global hooks across multiple applications, which was used as part of the guys' efforts against Samsung to find what particular file or what application was writing to a particular file. Then you've got Frida, for those that haven't used it, although it's pretty popular nowadays. Really quick and easy for prototyping and debugging and dynamic analysis of obfuscated code. So that kind of goes through our background to Pwn2Own, how we approached it, and some of the tooling, we ended up having to sort of try and develop to try and speed up our efforts. So now Alex is going to go through the vulnerabilities we found, how we exploited them.
So basically, James has talked about the approach and the methods we went through for actually finding these vulnerabilities. I'm going to talk about the actual vulnerabilities themselves. So what these bugs were, and basically how we approached exploiting them and chaining them together. So for Pwn2Own and for just exploitation in general, because like mitigations and things have improved, like sandboxing, that kind of thing, it's no longer possible to just be like one vulnerability or two vulnerabilities and an exploit, and like take those vulnerabilities and produce an exploit. It often requires you to jump through multiple different steps within the chain. So this is like from the perspective of logic bugs as well. So we got to assume that there's like no memory corruption. We're not doing like use after free plus sandbox breakout. That's like a totally different kind of attack. What we're going to do is, so the approach we took were initially to look for browsable intents. So the kind of things which were accessible from the web browser, which would allow you to basically pivot from the web browser into another application, potentially an application which is more vulnerable. We started off within Chrome. Chrome's got it's got a pretty good security team. It's got a quite good security history. It's quite difficult to find bugs within Chrome. So for us, it made sense to switch to as quickly as possible to another application or something to get code execution. So as James said, first stage is you browse to a website on the device. This triggers a browsable intent. So I started looking, I was analyzing through all of the browsable intents. There's not hundreds on the device because for attack surface reduction, the vendors actually tried to restrict this amount of attack surface. But I came across the Huawei Marketplace application. So this is essentially Huawei's answer to the Google Play Store. It's an application which it's got high permissions. It has installed packages permissions. So it's a good target for an attacker because it's a high privileged app. And it also exposes a browsable intent. So I was like, well, okay, this makes sense to start reverse engineering. So I started looking through it, looking through the application manifest, and I spotted that there was the browsable intent was this thing called HiApp schema. Hopefully you're familiar with Android, but basically what this says is the third API activity is it's an exposed browsable. Well, it's an activity which is allowed to be triggered from the web browser. And it registers an intent filter to say that it accepts like intents of a certain type. And one of these is the HIApp protocol schema. So if you've got HIApp : / then you can trigger the browsable intent. But Huawei tried to actually lock this down because they were, I guess they were aware that they didn't really want people performing arbitrary actions in the context of their marketplace application. So what they'd done was they'd implemented a whitelist, as you can see here, and this whitelist essentially it has 3 different domains in highcloud.com, vmail.com, and huawei.com. But if you look closely, they're using a regex to match the domain. So you're like, okay, well, our malicious content has to be hosted within one of these domains for it to work. But the regex matches, it's like .*, so it matches anything coming before highcloud.com. What this means is, it means that they didn't lock it down to use HTTPS either. So you could essentially use DNS poisoning and basically impersonating the highcloud or vmail.com domain, and this would allow you to load content in the from a HTTP site in the context of it would essentially treat it as if it was a whitelisted domain. So this was quite cool because this basically allowed us to load content into the web view in the marketplace. Okay, so what can you kind of do with this? Well, firstly, I want to talk about the actual protocol schema. It's a bit of a weird protocol schema. It's not something which is super intuitive. It took me a while to reverse engineer out the format of the protocol and how you pass parameters and so on to it. But they had the activity name which you wanted to call and the URI which you wanted to pass, and they used some JSON representation of the parameters. So this is pretty flexible because it allows you to basically pass parameters to activities on the device in the HIApp application. And one of these was the web view. So using this protocol schema, that's how we pivoted to the web view. At this point, we've now got our HTML page executing within the context of the marketplace application. the next thing was, okay, well, what does this web view allow you to do? Like, what's the actual benefit of doing this? It uses the HI space object, which is like a JavaScript, a Java object, which is used as a way of allowing JavaScript to call between JavaScript and native code. So you can go from JavaScript to Java code, and it's like essentially a bridge between the two. So I analyzed the JavaScript interface. You can basically only call methods with, which are annotated with the JavaScript interface now in the bridge. So they have to specifically annotate certain methods which they want to be called. So I was looking through the different methods in the attack surface for this. And essentially, I located one which was called launch app functionality. So this sounds pretty dodgy to me. I was like, yeah, okay, like, does this allow me to launch like any arbitrary application on the device from the web page? But I don't think they were intending to do this. I think they only really wanted like certain applications to be launched, but they use this intent parse URI functionality. So you pass your URI from JavaScript into the Java. Intent.parse URI is called on the URI to convert it into an intent URI. Then they use set package, and set package basically allows you to specify any package on the device. So we've got a pretty good exploit primitive there, because we can essentially pass we can craft our own URI, and we can basically craft the package for the application which receives that receives the intent. So essentially, at this point, you can call any activity on the device which is exported. So we've gone from just having browsable intents to now exported intents. We've sort of done the opposite of attack surface reduction. We've increased it. So, but this wasn't actually like super well known. There's a protocol schema called Android app URI schema, and basically this allows you to craft a Android app : / and then a package name, and then using the intent schema, you can basically embed extras. So if you're not familiar with Android, what extras are essentially the parameters which you can pass to activities or IPC methods on the device. And using this Android app schema, you can basically specify the parameters which you want to pass to the URI. But at this point, I was like, well, I kept looking at the marketplace application. We need to achieve code execution. Like, just having launching apps and stuff like that is not really good enough. And I kept looking at the bridge, and there wasn't any like obvious way to turn it into remote code execution. So the next thing to do was to basically, I started analyzing the other apps, which this new increased attack surface would allow you to now access. So this is what the URI looks like. So you craft the Android app URI with the parameters for the extra, for the intent. And then you call the window.highSpace object, which is exported within the DOM, which is hosted on our malicious web server. And at that point, we can now pivot into other applications. So you can kind of see where this is going, really. Like, I followed the same approach. I looked for other applications on the device which had, which I could trigger, which had more important, which would lead to code execution. One of these was the Huawei Reader application. Now, I wouldn't necessarily look at this because it was a low privileged application. It didn't really have that many permissions, but it looked like they'd done like no security on this application at all. So probably because they had the same thoughts as me. They were like, yeah, this app's just like, it's an ebook reader, like it's, yeah, like it doesn't have install permissions, it doesn't have elevated access. What's the worst of which can happen? But turns out this was like a mess. Like this had like every bad vulnerability you could think of within this application, because it obviously clearly hadn't been like tested or developers with security knowledge. So firstly, they had a flaw with the input validation, which allowed you to load a website up into the in this application, similar to the first one, but basically, yeah, allows you to trigger that web view. The code for this, I did the same process as before. I analyzed the bridge. I found this do command functionality within the bridge. What this allows you to do is, I think it's for like online reading of ebooks. So you can either download an ebook or you can like browse to it online. So I started analyzing each one of these, online reader and read now. Turns out that they had a directory traversal within the online reading functionality or the download functionality, which allowed you to specify the file name. So as you can see here, it does path.getBook directory plus v7.getString file name. v7 getString file name is a JSON parameter which is passed by the attacker. They don't do any path sanitization on the path. So essentially, you can directory traverse that. You can be like .. And at that point, you've got an arbitrary write. You control the content of the file, and you control where you write the file to. So you can be like .. /SD card or whatever, and then you can write outside of that. So that's pretty useful as well. I don't know how readable that is at the back, but that's the JSON schema for doing the downloading of the file. A little bit like when I was reverse engineering this, I tried hosting the file on my own web server, but they were doing some crazy stuff with with load balancing and AWS. So in the end, I couldn't spoof the protocol. So in the end, I just gave up and then hosted it on AWS, the payload, because it was just like taking me so much time to work out, to basically fix bugs within Huawei's HTTP implementation, because it wasn't adhering to the standards. So I was just like, yeah, I'll just do it, host it on a load balance thing as well. So yeah, at this point, we're like, okay, so we can arbitrarily write data to anywhere on the phone. Well, we can arbitrarily create a file to anywhere on the phone with whatever content we want. Surely that's game over now. Surely that's code execution. And in the past, in earlier versions of Android, you would have been able to overwrite the Dalvik cache and trigger re-optimization of the DEX loading and abuse the Dalvik cache. This was quite a well-known technique, but Google patched this. Google increased their security in later versions of Android. So I needed another way of gaining code execution. So I also had another restriction as well, which was I wasn't able to directly traverse and overwrite an existing file because there was some checking to see if the file which you were writing to already existed. And if not, it would basically prevent you from writing this file. So I couldn't just overwrite a config file or an existing jar file or something like that. So I was like, well, what can I do now? And what I was like, it'd be really good to see if there was if they'd exposed an arbitrary delete primitive. I don't know why this would exist, but I actually found one, which was also vulnerable to directory traversal, which was kind of useful. But as you can see here, it calls file is_exists and checks the path.getBookName check open, which basically, so that checks to see if the file exists and into the function. And if it does, then it calls file.delete on the path. So looking more into this getName check open fail function, essentially it gets the open fail directory and then appends it with an MD5. So this is a way of caching. They use cache files and they use the MD5 name of the file as the cache. So I was like, hold on a minute. We control both we control the file name. So we can pre-calculate an MD5 hash of the file name. Why don't we just pre-calculate an MD5 hash of a directory traversal file name or file path? And then that'll get appended to the book directory. So what that looks like is, so that's the hash of MD5 hash of /plugin/df services/classes.jar. And then when that code runs, if we create a file within, like in the right location using our arbitrary write primitive, then essentially the directory, the delete will trigger the deletion of this jar file. So at that point, I want to be like, okay, well, like we can replace the jar file. So where the jar file came from as well was in the Huawei Reader application, they implemented like additional functionality for loading plugins. So it was an ebook reader, but it also handled things like text files, PDF, and things like that. And for some reason, they were loading jar files like off the SD card, which is pretty bad because the SD card is globally writable in certain directories. And so that means that, but I mean, we're already executing in the context of the app, so it doesn't really make too much difference, but they're still loading a jar file from there. It's not in the sandbox. It's not somewhere where we wouldn't be able to write to. So this is what this code does. It uses the Dex class loader in Android, in Java, and basically, loads classes.jar from this directory, which is on the SD card, which we have write access to, and then calls, and then creates a new instance of the object which is loaded from the jar. So, putting it all together, so at this point, we can override the jar file, but there's another issue is like, how do we get the jar file to actually load? Huawei had implemented another method for like triggering loading of the jar file, and loading of the plugin. Basically, if you access a file of like TXT type, it would essentially trigger the loading of the jar file. So at that point, your malicious jar file can be loaded, as long as you create the payload in the correct format. So that's the code for the payload. Essentially exposes the doc feature class and executes a remote busybox shell using netcat. And at that point, you've got a remote shell running on the device, so you've got code execution. So it's game over. So I've got a demo of this as well, what this actually looks like in practice, if it plays. So this is going to be pretty quick, but essentially, this is loading the website from the malicious web server. Then it's creating the hash to trigger the download of, to trigger the directory traversal of the, which will be used to trigger the directory traversal of the jar file. Then it's pivoted to the Huawei Reader application, loaded the jar file. Then it's triggering the plugin loading to load the plugin, and then finally executing busybox and starting the netcat listener. I understand I've gone pretty quickly through this vulnerability, but we've got a white paper basically outlining all of the steps, and I've also published the code for the full exploit as well, end to end. And then that's code execution at that point. So, yeah. Thanks.